Hi, so I'll present joint work with Lorenzo Clemente, and our paper is about the universality problem for ambiguous register automata. So register automata is a model of computation over infinite alphabets, and these are just finite state machines enhanced with a finite number of registers that can store previously seen values. And those values can only be used to be compared with the letter that is seen for the equality relation and nothing more. And the universality problem is the problem of whenever you have a given instance of a registered automaton, does it accept every word or not? So in the first part, I will introduce the model, mainly with examples. And in the second part, I will present an algorithm to decide the universality problem. Note that it was already known thanks to Mote and Quas, but our approach is totally different, and it gives a better complexity bound. Okay, and our approach is first we use the structure of the automaton to count the runs on it, and then we study those countings thanks to non-commutative linear algebra. So first, the model. So here is the first example. So the alphabet is just the natural numbers, and there's only one register. So here there are three states, three control location. Let me show you how it works with an example. So let's assume that we read the word 01501. So first, the registers does not contain anything. It is undefined. And it takes this transition, which means we store 0. So this is what we do. We are in the second state with 0 stored. And here there are two transitions, the self loop and the loop to state 3. And the self loop says that we can only take this loop if the letter that we read is the same as the letter that is stored. And it is the opposite from this transition here. So we read 1, 1 is different than 0, we go to the last state. And here it's the opposite. We can take the self loop if and only if the letter that we read is different than 0, and otherwise we go back to the second state. So we read 5, we stay here. We read 0, we go back to the second state, and we read 1, we are in the last state. So this word is not accepted. And this was an example of deterministic automaton. But now we can allow for non-determinism in the transition. Let's say that given a control location and a content of registers and some letter that we read, it is possible that we may be able to take several distinct transitions. So here, this is the case here. The automaton has to check to guess deterministically which transition it takes and when it jumps to the second state and store the value. So this automaton here recognize the set of words that have twice the same value somewhere. So what it does is that it guesses non-deterministically the first appearance of a letter that appears twice. It stores this and then it is accepting when it sees it for a second time. Note that the complement of this language is not recognized by any register automata, so the world model of computation is not closed in the complement. But also, we are not allowing non-determinism in register. That did say that we can only store previously seen values, and we cannot just guess them and store arbitrary values. So now, about what will really interest us is the unambiguity property. Let's say that for each word, there is at most one accepting word. So this is a very important property that is widely studied because this induces a bijection between accepting runs and accepting words. So we can intuitively count. So here is a first example of an ambiguous register automaton. So it is unambiguous because given any word, if this word has the same letter, which is the same first letter, which is the same as the last letter, well, then it can only take the upper path. And if the first letter and the last letter are different, then it can only take the lower paths. So this is an unambiguous register automaton. Now, it is in the title, we want to solve the universality problem. Let's say we have a given unambiguous register automaton, and we want to know whether it accepts every word or not. So this problem is important because of its relation with two other fundamental problems. The inclusion problem, you have two register automaton, you want to know whether the language of the first one is included in the language of the second one, and the equivalence problem, you want to know whether the two languages are the same or not. So it is very classic and simple to see that if we can solve inclusion, we can solve equivalence, and if we can solve equivalence, we can solve universality. But in this paper, we show also that if we can solve universality, then there is a p-time reduction to inclusion. And this is quite surprising because even for deterministic context free grammars, universality is decidable but not inclusion. So there is no such reduction. And I won't present the details here. So the main result is that the universality problem for unambiguous register automata is decidable. So it was known by Motet and Quas that it was in 2x space. And in this work, with totally different methods, we show that it is in 2x time. And since we did this work, there has been unpublished development of Boyanchi, Klein, and Moorman, and they were studied weighted register automata. And they developed a theory of vector spaces spanned by orbit finite sets. And they showed that this universality problem for unambiguous automata with guessing, so a register can guess a value and store it, and they also extend registers so that you can compare them also with the order relation, and that it is decidable in X time. So this is quite a nice improvement. And also the whole problem of universality problem for register automata is undecidable in general. So this motivates this work of the universality problem for unambiguous register automata. And what we do here is that we extend Schutzenberger continuum approach. And we hope that we can generalize this method to yet other data domains. So now let's solve the universality problem. So as I said, we want to count. But when you fix a length, the set of words of a given length is infinite because the alphabet is infinite. So we need to restrict a bit what we count. So what is an orbit? The orbit of a word U is just the set of all the bijection of this word. So this means that the word 112 will have its orbits that contains 223 and 334 or 332. And indeed, it will contain every word such that the first two letters are the same as the first two letters are the same, but the third letter is different. So now, when you fix a length, the set of words of length k has finitely many orbits. And in fact, they have the kth Bell number many orbits. The kth Bell number being the number of partitions of the set of naturals between 1 and k. So now we can count. So you have a given register automaton, and take S that is a configuration. That is to say, this is the data of a control location, a state, and the content of the registers. and you take that up to orbit because you want to have finitely many configuration. So let's count. Well, we count all the run that ends in S and that start in some initial state. We count that up to orbit because again we want something finite. And well, the first parameter is quite obvious. It is the length n, but we need a second one because only with one parameter we cannot put some good equations on the counting function, so we cannot manipulate them. So we need also to add k, which is the number of distinct letters on your run. So here is the first example. This is the most simple automaton. It is just one state with no register, and it just accepts everything. So here, the counting function satisfies this recurrence equation. Because take a run of length n plus 1 with k plus 1 different letters, well, there is a disjunction between if the last transition that was taken has seen a letter that is fresh or not. Fresh meaning that it was not appearing anywhere in the word before. So if the letter was fresh, well, you can extend any run of length n with k different letter into a single word of length n plus 1 with k plus 1 different letter. And if the letter was not fresh, well, now you have more possibility. Indeed, you can extend every word of length n with k plus 1 different letters into k plus 1 different runs, because you can just choose any letter appearing in your word. So this gives k plus 1 possibilities. And this gives precisely the Stirling numbers of the second kind for those who already know it. So now we can apply that kind of counting to every register automaton. And we count runs, but because it is unambiguous, what we really count is accepted words. So fblue of n plus 1 k plus 1 is 0. It's corner cases because there's only the empty words that end in blue. So we do not really care about this. And now about fred. Well, again, it's this disjunction between which transition was taken last. Was it the self loop or the transition from blue to red? If it was blue, we have fblue of nk plus k plus 1 fblue of nk plus 1, which is here for the same reasons as for the Stirling number of the second kind, fresh or not fresh. And for the self loop, it's again the same, but it's a bit different. It's a k and not a k plus 1. This is because there is one letter that is stored here. So when you are in the non-fresh case, well, you cannot choose k plus 1 different letter because one of them is stored and you cannot pick this one. So this gives only k different choices. Now, for green, well, the blue part is the same as before. And now the self loop, you can take it whenever you see a letter that is stored. So obviously, you can extend uniquely every run of length n with k plus 1 different letter into only one run of length n plus 1 with k plus 1 different letters. So this gives this factor here, f green of nk plus 1. And for f orange, it's a combination of both arguments. There is a stored case, f red here, and the green case with fresh, the first f green, and not fresh, the second f green with k. So this gives what we call a lean-rec system. That is to say that there are several auxiliaries sequences, and one of those functions at n plus 1 k plus 1 is just a linear combination of the other functions at nk plus 1, nk plus 1 n. And the coefficients are not necessarily constant, but they can be any polynomials in k. And there also are some initial conditions so that everything is uniquely defined. Now, as I said, we want to reduce the universality of reduce automata to the zeroness problem of those linear sequences. That is to say, take a linear system, pick a function, and some initial condition. Is this function zero everywhere or not? So how are the two problems related? Well, first compute the Stirling numbers. It's linear, and it computes the orbit of all words of length n and with k different letters. And then your automaton will be universal if and only if for all length and number of different letters. Well, f for range, let's say the sequence that uh, correspond to the final state is just it's just the Stirling numbers, because you want that it accepts everything. And because linear is closed by subtraction, you just have to check that f range minus s is zero everywhere. And again, I want to stress that this works because the automaton is not ambiguous. So there's bijection between accepting words and accepting words. So now we want to study those linear sequences. So we want a more suited form for manipulation. So we would model those kind of recurrence equation by operators. So for instance, f of n plus 1 k plus 1 will become shift 1, shift 2, and operators applied to f. Shift 1 being the operators that take sequence, a bidimensional sequence, and add 1 to its first coordinate. And shift 2 just do the same to the second coordinate. So for instance, a k plus 1 times f of n k plus 1 will become the operator k plus 1 times shift 2 applied to f. And so because this space of operators as a ring structure, well, you can just factorize everything and have a big operators applied to f. And this is what we will call an OR polynomial due to the work of Einstein OR in the 30s. But so we have a ring of operators, but this ring is not commutative because you can see a polynomial as just an operators that multiply your sequence by this polynomial. And so multiplying by a polynomial and then shifting is not the same as shifting then multiplying by these polynomials. Because in the first case, you will also shift your polynomial. So this is a ring that is not to the standard and a bit complicated. But with those, we can model linear. So this will be just a system of equations with some variable, the fi, s, which is the Stirling number of the second kind, and g that just contains f range s minus f range, and the coefficients that are operators. And what we want is to find an operators that just cancel the g. And we want to get rid of all the auxiliary sequences, because what we want is to check that g is zero everywhere or not. So if we were in the field case, like say the real numbers, well, we could just get rid of the leading coefficients in front of f blue, and then subtract f blue everywhere. And then we would have a sequence with less equation and less variables. And we could just repeat that again and again. And this is what we will do, because our ring of operators has a Euclidean division and as a Euclid's algorithm. And what will really interest us is that then, if you take two operators, well, you can always find a common left multiple of those two. So it is a short example, but it's just to show you that even starting with two very simple operators, the common left multiples can be more complicated. So it's not totally trivial that this ring admits common left multiples. So now we can do what I just said, eliminate the, the variables one by one. So first you multiply by shift 1 the second and the third line, so to match shift 1, shift 2 here. And then you add the first line to the second and third line. And so you will just get rid of, of f blue everywhere. So you will have a system with left equation and less variables. And you can repeat that again and again until you just have a canceling relation for G. You have uh, you have an operator that cancels G. So now what do we do with that? Well, what does it mean? It means that G of n plus 3 k plus 3 is a linear combination with point coefficient of G of n plus 3 k plus 2, etc. And so this means that if G of n plus 3k plus 2, G of n plus 2k, etc. is 0, then G of n plus 3k plus 3 will be 0 as well. So it will be enough to check that G is 0 on a straight lines parallel to the axis to conclude by induction that G is 0 everywhere. There is just a small details, is that there is a leading polynomials that has roots. So when we are on these roots, we cannot say anything about G of n plus 3k plus 3. So we first have to step out of those roots to conclude. And we can do that because it's a univariate polynomials, and hence it has finitely many roots. So this algorithm here gives a 4x space complexity bound, which is a lot and not what I promised earlier. And this comes from Lagrange bound that relates the zero of polynomials to the value of its coefficients, and that we can check zeroness of section very efficiently of a straight lines. And this stands intuitively because it is in dimension 1, and hence it is easy. So we can do better. I won't give many details here, but intuitively, instead of removing one variable at a time, we just want to consider the linear system as a matrix of operators applied to a vector of bidimensional sequences. And I just want to invert this matrix by using non-commutative linear algebra. So we will put the matrix of operators in a triangular form called the Hermite form. And then we can just pick the rightmost, downmost operator that would cancel G. And a paper of Gisbrecht and Kim gives us good bounds on the coefficient on this triangular form. And this will give a bound on the length of the short witness. That is to say that we do not construct explicitly any empty form. What we do is that it gives a bound that says if every word of length less than k are accepted by the automaton, then the automaton is universal. So our theorem are that the zeroness problem for linear sequences with univariate coefficients is decidable in only x time. And so for the universality problem for unambiguous automata is decidable in 2x time. And if we assume that the number of registers is the constant of your problem, then it gives only x time. And we can reduce that to x time and p time respectively if some conjectures called the monistic conjecture holds. So what is this conjecture? Well, is that what made the complexity blows up is this leading polynomial here and its roots. So we conjecture that we can always find canceling relations without leading coefficients. And this will give an x-time bound, which will match the result of buoyancy, clean, and movement. And also, we would like to extend our approach to other data structures, time automata, page automata, and even to weighted automata. So here are some useful references, and thank you for your attention.